So what is a heating curve? A heating curve is a graph that helps you to understand the phase changes that a substance will undergo. The phase changes that a substance will undergo. This is the heating curve for water. For water. What phase is in black? What phase will you find water in when it's below 0 degrees Celsius? Solid. For water, water is called ice when it is a solid. So this is solid. What do we call water? What do we call water when it is between 0 and 100? Liquid. What do we call water when it is above 100? Gas. If somebody came up to you and told you, I am a chemistry terrorist and my job is to terrorize you, you have two choices. You can either place your hand into boiling water or put your hand into a container of steam. And those are your only choices. The alternative is that you have to sit in a beaver concert. Bieber concert. I was thinking beavers. I didn't know beavers could sing. Okay. Which one would you choose? Steam or boiling water? Are you kidding me? Do you know what your skin what will happen to your skin if you put it in boiling water? Kids, what? You had your hand up. Boiling water or steam?
Boiling water.
Why?
Because steam is it's hot air. I mean, it's hotter than boiling water.
What temperature does steam have to be in? Above 100. What temperature does boiling water have to be in? 100. Okay?
I don't like Celsius. I like
So, let's use Ruthie there as an example because she's between Lenoir and between Morgan. So this is Ruthie. Describe Ruthie microscopically when she is negative 20. Is she held in place or is she moving around? Because she's held in place. Is she vibrating or not vibrating? She is vibrating. She will not stop vibrating until she reaches what temperature? Actually, it's negative 273 degrees Celsius, 0 Kelvin. So, the closer she gets to negative 273, the slower she will move until she gets to 0. Okay, but she's nowhere close to 0. She is at negative 20, which is actually pretty dang warm compared to negative 273. So at negative 20, she's still in place, but she's vibrating. What happens to her if I get her to negative 10? She's vibrating faster. What happens when I get her to 0? She could now maybe do a little bit of a dance here, move a little bit further away, but when she does, she bumps into Morgan and into Mark. When she bumps into Morgan and into Mark, what does she do to her energy? Gives them a little bit of energy. So because she is interconnected with them, and with Calhoun behind her, and with Beth behind her, she has no choice but to lose energy every time she bounces into them. So what's happening to them as they're bouncing into Ruth? They're gaining energy. Okay? So the energy I'm supplying Ruth is beginning to spread out to Calhoun and to Morgan, and now they're able to move around. And they're able to bump into you. When they bump into you, what happens to the energy?
They transfer to you.
But I pretty soon, mortal here will have energy from the energy that I gave only to Ruth. I said, Ruth, here, take this energy. This energy is only for you. So 20 minutes later, I come over here and mortal's going, I have energy. Where did you get that energy? Probably not through Ruthie, but probably through Allison and Esther and Natalie. Where did they get it from? From Grant and Sasquatch and Max. Where did they get it from? From these guys. Where did they get it from? So do you see why when you start melting, I keep adding energy, but does it look like anything's happening? No, because what are you doing? You're taking all this energy and you're spreading it out in order to be able to melt. Melting is the storing of energy, potential energy. When I was giving her energy and she was vibrating faster and faster and faster, that was kinetic energy. But at the point where she started melting along with everyone else, that became potential energy. To me, it looks like the temperature is not changing. But was there a change in temperature? Yes, energy was flowing from here to where mortal is. Microscopically, there was a change in temperature. And if you were to actually measure this digitally, what you would find is that this line goes up and down, and it's not a straight line. But take the graph and step back, what does it look like to us? It's a straight line. Yes?
Wait, but what about like when water gets like below freezing and it's still water, you know what I'm saying? Like you put like a bottle of water in the freezer and it doesn't freeze, you can like pour it out and it freezes.
Distilled water, you can like smack it on the table at exactly 32 degrees.
We'll talk about that. In order for something to freeze, it requires what we call a seed. And it needs something to freeze onto. Okay? So you can actually, it's called supercooling. You can actually cool something below its freezing point without a seed for it to freeze onto. It won't freeze. That's why, sometimes in order to get, if there's a lot of moisture in the air but it won't rain, they'll actually get on an airplane, they'll seed clouds. All they're doing is discharging these tiny little particles in order to allow the water to condense on the particle and then become little raindrops. That's pretty complex. What you're talking about is a very unusual situation. Next. Okay, so here, you guys, now Ruth can come over and talk to Stefan because you guys are liquids. You're still interconnected, but you can actually move around quite a bit. There are limits. If Ruth is going to come over here, then Morgan and Mark are going to have to be in this general vicinity as well. Actually, to tell you the truth, microscopically, what would happen is that Ruth would disconnect momentarily and then come over here, connect with Marie, connect with Phoebe, disconnect, connect with Grant, connect with Max, disconnect, connect with Esther, connect with Allison, and then connect with Stefan. See what's going on? Can you see it in your head? Okay? You have to be always connected if you're a liquid. Then we come over here. What happens to Ruthie if I increase her temperature to around 30 degrees? Can you see it in your mind's eye? What is she like? Is she still connected to you guys?
Yeah.
Yes, but how is she moving? She's moving faster. Okay, now it's no fun to talk to Ruthie because, and then she runs over there, and then she runs over here. It's like Hammy on Over the Hedge, right?
Oh yeah.
Okay, what happens if we get her to here?
She's not connected anymore.
At this point, she looks at you and goes, breaks the connection, and goes running out of the room. Okay, and then I'm going, okay, I was giving her energy, now where's my energy? The energy is gone. She took my energy. Okay, so she reached this point, and there goes Ruthie. I go, well, okay, fine. I'm going to give Mark. Mark is over here. I'm going to give Mark some energy, so he starts going up, 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 and now he does. So why does it flatlines again? In this case, you guys all had to, because you were all interconnected, what you had to do with the energy was spread it out. But now, do you have to spread it out? Because you're taking the energy with you. Why is this line 7 times longer than this line?
Because it's like a.
Because Ruth isn't sharing the energy.
There is no sharing. This time, I just needed to give you enough energy for all of you to begin to slide past each other. Now, I had to keep adding energy. What happens to a pot of boiling water if you stop adding energy? Stops boiling. It's not something that you can get started and then it'll go off by itself. You have to keep adding energy until everyone has turned to steam. And then what can happen to the temperature? Once I get you guys all corralled in a different room there, you guys are all bouncing off the wall, literally. What happens if I start turning up the temperature of the room?
You start sweating.
You guys are molecules. You don't sweat. What starts happening to you guys? Yeah, you start moving faster, bouncing more. Okay? That is a heating curve. What happens when I start removing the energy?
You go down.
Start slowing down, start slowing down. What happens here?
You start connecting.
You start connecting with other water molecules. What happens here? Slowing down, slowing down, slowing down, start slowing down. At this point, you're still connected. What's happening here?
You're sharing. It's not as much, right?
Now you start finding your locations, and you start stopping in place. Until you're all stopped in place, and now what happens?
You just stop moving as much.
You stop moving as much. Good. Heating curve. So why does the temperature stop when solids melt? All the energy is flowing from the warmer molecules to the cooler ones. The average is 0. So as you're melting, does that mean everyone will have the same amount of energy? On the average, it'll be at 0. There's going to be warmer ones like Ruthie. There may be cooler ones like Stefan. But on the average, it's 0. Why does the temperature stop when the liquid boils? The energy that could have continued the heating is being taken away by the molecules that are vaporizing. Okay, do you understand? At what points are you storing? It appears as if you're storing energy, potential energy. What points do you have potential energy?
Water and steam, nice.
The flat lines. At what point do you actually see your energy doing some work?
The straight line, the horizontal, the diagonal.
So is it
Does that make sense? Potential energy is when you're adding energy and it doesn't look like you're adding energy. Kinetic energy is when you're adding energy and it looks like you're adding energy. What is perhaps the most interesting feature of water? The fact that its solid is less dense than its liquid. I cannot stress enough how freaky that is and how important that is. Let me show you.
The ice bomb illustrates the fact that the volume of ice is greater than the volume of an equal mass of liquid water.
Folks, that's a grenade. Its job, you normally have an explosive. Once that explosive is triggered, pieces of metal go flying in every direction. If you're caught in that path, you are Swiss cheesed. That's why grenades are
Some cold
so
water is poured into a
dangerous.
cast iron bomb, and a
But the
threaded plug
explosive
is
has been
screwed into
removed.
the
Everything's
bomb so
okay.
that the bomb is tightly sealed.
And not only that, but they replaced the explosive with nice, safe water. So they fill up the water all the way to the top, and now they're going to clamp it shut. They're now going to place this nice, safe water. Don't be working on your homework.
The bomb is
please.
then placed into a dry ice
They're going to
acetone
place this
slush,
nice,
which
safe
is at
water
negative
into a
77
water bath
degrees
that's
Celsius,
at negative
and will
78
cause the water
degrees.
inside the bomb to freeze. A wooden box is placed
Run.
over the top of the
Run.
bomb and slush bath. It takes a short time for the
Safe
water to freeze.
water.
When it does, the bomb explodes. Some of the dry ice acetone slush is blown onto the explosion shield.
Why did it blow up? Well, no, there
Little
are
bits
pieces.
of the cast
The
iron
reason
bomb
why they
are
put
left.
why did they put the wooden box there?
When the water freezes, tremendous
They didn't want
pressure is
grenade
produced.
fragments to go flying through the
The
air and kill
pressure
the
is enough
cameraman.
to cause this cast iron bomb with
Look at
more
that.
than 1/8 inch thick side.
Nice, safe water. Why is that illustrates something that's so important? First of all, for us driving around town.
Oh, because wherever it goes in potholes.
It's what creates potholes.
Yeah.
Okay? So it rains, the water gets into the cracks. What happens when that water freezes? And then you drive over it, the weakened concrete. What happens when you drive over weakened concrete? It cracks it even further. Pretty soon, whole chunks of it is being brought up, and you have a pothole. Okay, so for us, it's a big bad thing. For Mother Nature, it's a life-bringing thing. Why? Because you've got rocks and boulders all over the place. Those boulders have minerals that plants need. Most plants can't access those minerals. Over time, boulders get cracks in them. So what happens during the winter time when the water gets into the cracks and freezes? It busts the boulder. So bits and pieces of boulder minerals go flying into the water, into streams, which makes its way into the soil. Now do plants have the nutrients they need? If it wasn't for the fact that ice is less dense than water, life could not exist here on Earth. For us, it's an inconvenience. For plants, it gives them life. How about boiling versus evaporation? Okay, so show me, where on this graph does boiling take place?
Water and steam.
Where on this graph does boiling take place?
Water and steam.
Right here. That's boiling. Where does evaporation take place? Anywhere on that line, evaporation can take place. What's the difference? What happens when something evaporates? Yes?
It's where like the molecules, since they're moving so much, they break off and go off.
Okay, so Ruthie's at the surface. You're absolutely right. Ruthie's at the surface, and I pour so much energy into her that she goes nuts. Breaks away from Morgan to Mark, and then flies away. Ryan is deep inside the water. If I was to aim my energy at Ryan, what would happen? It would hit Morgan, disperse, maybe hit Alec, disperse, and by the time it gets to Ryan, how much energy is left? Okay, so there's two ways. The only way I can get Ryan to become a gas is if I give everyone heat. And slowly I get you up to 70, 80, 95, and Ryan is deep inside the water, and he's at 100. Now he can become a steam. Any other way, the only way you can become steam is if you're at the surface and I pour a lot of energy into you. Okay? Case in point. Bottle of water. I open it. I leave it sitting there. In a month, this much water has disappeared. Did somebody drink it? Hopefully not. What's happened to it?
It went away.
Well, we usually use the word evaporated. Okay? It evaporated. Why? Just a little bit. It's been out in the open for a month. Go.
Surface area.
Very little surface area. So what happens if I take, so it might take this much water, it might take a whole year for all of it to evaporate. Or I could ask you guys, get out of this room. I tell the custodian, just leave this room alone, take the bottle, and sprinkle it all over the room. By tomorrow morning, where is the water?
Gone.
Why?
It went away.
In order for it to evaporate, it needs to be in contact with the environment. All right.
I've never gotten to absolute zero this morning.
They've come fractions. Very, very close.
Possible because absolute.
They think it is.
So like, what are they making cold? Like water or what? Air or what?
You'll have to get on the net. I don't know. Are phase changes chemical or physical changes?
Physical.
What is actually being separated in a phase change? It's just the bonds holding them together. The rope that's holding you guys together. If a phase change was chemical, what would be breaking?
Bonds.
Okay? If I want Ruthie to undergo a chemical change, okay, I would have to tear an arm off, tear the head off, tear a leg off. I'm not going to demonstrate that. Okay? But if I want Ruthie to get away from Morgan, all I would have to do is cut loose the rope that's holding them together. That's just a physical change because you still have two human beings. There are very strong bonds holding Ruth together. We call those intramolecular bonds. Intramolecular bonds. Okay? So 13.4, I expect you to know the difference between inter and intra. Let me give you an example from the computer world. I've had the opportunity to be old enough to know a time where there was no internet. I remember sitting in front of a computer thinking it was so cool that by pressing a button, I could see pictures of the Louvre. Paintings that can only be found in the Louvre in France. I thought it was so neat that I was in the computer in Paris, France, using the internet. My computer at West High School was connected to a computer in Paris, France. We called that the internet. Now, in the same way, my computer could access my neighbor's printer. I don't know how. So what I would do, and he could access my printer, and he was a big football fan, and I would send him little Star Trek messages just to irritate. For the longest time, he did not even know that I was the one doing it. Okay, because I would deny it. He would come up to me, are you accessing my printer? No, what are you talking about? Well, somebody's leaving Star Trek messages behind. I don't know what you're talking about. So, what was I doing? I was accessing the intranet. So, I was in West High School where there was computers and printers, and they were all interconnected. They do not use the word intranet anymore because it confuses people with internet. And most people are ignorant and they don't know the difference between intranet and internet. At that time, it was easy for the internet to go down. The internet was very much an experimental thing. So here I am at West High School in Knoxville, and I would take the internet in order to get to Paris, to the Louvre in, and I'm not sure if this is pronounced right, or spelled right. This is West High School. So I would use the internet. Back then, it was, the internet is down was a common phrase. For us now, that's rare. Somebody must have gone into Google, somebody got into Yahoo, somebody got into somebody big and brought things down. And usually I don't think it's ever brought down. It might just slow down for a while, right? Okay? It was hard to bring the intranet down. Even when I could not access SACM, which was the supercomputer at DOE, I could still access my buddy's printer and irritate him. Okay? Why? Because the connections inside a building are very strong, but the connections between buildings is very weak. So intermolecular bonds holds molecules together. Intramolecular bonds holds a molecule together. Okay, I don't know how else to say it. Holds the different parts of a molecule together. This is very strong, and this is very weak. Some examples of what holds this together would be ionic, covalent, metallic. We've talked about this. Okay, this is intermolecular. Let me show you this picture right here. Okay, so here is Ruthie, and here is Morgan. They are held together by intermolecular bonds. But Ruthie is made up of two hydrogens and an oxygen, and she is held together by intramolecular bonds. Very strong, very weak. Do you see the difference? Now, on Thursday, I'm going to show you the different types of these things. I've actually already taught you most of the different types of these. It can be either covalent or ionic, and then I'll introduce metallic at the end of the chapter. What kind of motion can intermolecular bonds, the ones holding Ruth and Morgan together, what kind of motion? What do we see going on? It's this kind of thing. What do we call this? Yeah, okay. But actually that's called vibrational. Vibrational. So what happens to this vibration as you increase the temperature?
It gets more and more.
Until finally what happens?
Right.
In boiling, you have so much energy, so much vibration, that it finally snaps. Okay?